Olivia, take on.
Hi everyone. So my name is Olivia. I'm a fifth year PhD student advised by Fred and Kunle Olakotan, and today I will be talking about mapping sparse applications to accelerated computing systems. Normally I say I'd be happy to take questions during the talk, so it's a little more interactive, but you know, we have a panel session after, so maybe I'll hold questions till the end. So to put this work in context, there has been a whole history of programming systems for dense domain-specific accelerators. They're ubiquitous, and we often use them without even knowing. But there exists really no such system or no such ecosystem for sparse applications and for sparse accelerators. And that's exactly what I'll be talking about today. So I originally had a motivating slide on like why sparse applications are important, but I don't think we need that in this room for this audience. So sparse programming systems research and development is lagging behind that of its dense counterpart because there are some more challenges that we have to face. And this is also stolen from Fred's slides, but there's a bunch of complexity in what we want to compute, including through the algorithm or expression, this specifically for sparse tensor algebra. But there's further complexity in the scheduling, so there are scheduling optimizations that you can do in dense land, but actually in sparse land there are more sparsity-specific scheduling optimizations you can do. Now you can tile by different factors instead of just that impact performance more, as an example. And then there's also the compression formats that you care about. So there are data structures that originally you don't have to handle, and also the dependence on data for your performance. And for a general programming system, you actually want to handle the Cartesian combination of all of this, and it's impossible to do by hand. So this really means that things should be managed automatically through a compiler if we want to handle the whole entire domain and do it well. And so prior work compilers have compiled from high-level languages down to generated sparse codes, but these sparse programming systems are for CPU-only codes. So here I show CPU code for sample dense matrix multiplication, or SDDMM. And you don't really need to understand this code. This is generated by Taco. All you need to know is that it's really complex, and I certainly wouldn't want to write that by hand, right? So the compiler is already handling it for you. And so there's all this prior work that we can leverage, but why do we want to even support these sparse accelerators? Well, they're actually promising for accelerating sparse computation, and we've seen this popularity start to happen both in academia and also in industry, for example, through sparse cores on the TPU, in the GPUs, and also the Meta MTIA, or the training and inference engine that also supports sparsity. And so not just through popularity am I going to motivate you, but actually benchmarks show that accelerators can improve performance as well. Here I'm showing sparse matrix addition, and I show the performance for Taco. And also we show like, okay, we have some high performance libraries that can also express this kernel, and because the data changes, you know, no system dominates. So it really motivates the need that you handle both. But on the other hand, we have some sparse accelerator from academia and from prior work, and it shows that actually, you know, maybe the accelerator can outperform a CPU by over 2 orders of magnitude, right? Because you have parallelism and pipelining, and then you also have things like lower overheads because these accelerators strip away all of the things in the CPU that you don't need for these sparse computations. And so the accelerators, though, I already said, like, sparsity further complicates these programming systems. Well, accelerators will further complicate it even more because you now need to consider how your CPU host, or in any distributed system, how you offload data and computation onto your domain-specific accelerator. And on top of that, you actually have to program and configure the accelerator itself, if it's programmable, and even if it's a fixed function ASIC, oftentimes they come with many configuration files. And if it's not programmable, you need to figure out what hardware constraints, you know, like what hardware constraints are there in that accelerator, and you need to be able to match those constraints. And so how do we program these accelerated computing systems? And I really just mean a computing system accelerated with an accelerator. And this is through the compilation systems that address both programmability and the mapping problem from different levels of the abstraction. And when I say different levels of the abstraction, I really mean different levels of how we think about the computing system abstraction. So the first level is through thinking about our accelerator as a black box. And so I will talk a little bit about Mosaic, which is a compiler that we presented last year at PLDI, and it really allows you to offload data onto your accelerator, treating it like a black box. And then I'm going to talk about the sparse abstract machine, or SAM, which configures and programs the accelerator itself. And then I will talk about follow-on work stemming from SAM, where we actually built a new sparse accelerator. And so first, let's talk about Mosaic, offloading computation onto accelerators, treating it like a black box. So again, starting with our SDDMM CPU code example, it's already so complicated. But the problem is that there may be an accelerator that can do an expression that you'd like to accelerate. So for SDDMM, maybe we have some accelerator that can do sparse, dense, matrix element-wise multiplication. So that's a sub-expression of the total expression you want to compute. And because it's faster, you know that you can accelerate your full expression. OK, so what does Mosaic do exactly? Well, first we need to identify the code or the sub-expression that the accelerator can compute and isolate that sub-expression from the code. Then we need to actually slot in the accelerated API call, right? And then also offload that computation onto the accelerator itself. So that's many things to do that maybe a user would not want to do, especially if they have many accelerators and they want to do this for many types of expressions. So Mosaic does exactly that. Mosaic allows users to programmatically describe the capabilities of their accelerator so it can automatically find ways to utilize that accelerator. And how exactly does it do this? Well, Mosaic programmatically describes accelerators using its external function interface, which is a plug-in system where users can plug in different accelerators or external functions. And then using that, users, so the external function interface describes an accelerator in two ways. It first describes what does that accelerator compute, and then it also describes how exactly to target that accelerator. So how do you call that accelerator using its API? And then users can manually use these accelerators by manually writing schedules. So maybe you want full control and you're a performance engineer, you know exactly what to do, right? I can schedule this, I know that I want to target this sub-expression. And then Mosaic will validate that the binding is correct using a solver-based approach. But if the user isn't really familiar with the accelerator or the function that they want to plug in, Mosaic also has an automatic search mechanism, which will then, given a full expression, look for all of the sub-expressions that it can replace, given all of the accelerators that the user had plugged into the Mosaic system. And although I've been talking about Mosaic in the context of accelerators, like Stardust shown here, it actually generalizes to all high-performance systems as long as it can do some external function call. And then to reiterate, through composition of the high-performance systems, and Mosaic has a default code generator to fill in the rest of the code, and through a compilation path, the compiler is able to generate the code that you want for the end-to-end expression, calling the accelerator or high-performance library call that you want. And then actually the numbers that I showed to motivate a sparse accelerator in general, these were all generated through the Mosaic system. So Mosaic was able to call through its default code generator Taco, but then was also able to call Intel MKL through an external function interface and our sparse accelerator through an internal function interface. So what that allows you to do is it allows you to use independent systems all in one system, right? So you can generate numbers and comparisons, but also it gives you a higher level of representation for accelerator programming. And Mosaic automatically takes care of the rest. But now that I've presented a programming system that can call the accelerator as a black box, we need to answer the question of how do we actually program the accelerator itself? There needs to be a way to describe actually the fine-grained computation and mapping onto our accelerator and the fine-grained data flow, as we call it, or the computation ordering within our accelerator. So we do this through the sparse abstract machine, or SAM, and this was work presented last year at ASPLOS. So, So to motivate the need for finer grained representation of accelerators, let's consider the performance implications of data flows, or in imperative loops, loop reorderings on sparse computations. So by data flow, I specifically mean the processing order of all of the indices, which will modify where the sparse filtering mechanism occurs in our computation. And so that will impact where the compression skipping occurs. These filtering mechanisms specifically include intersections and unions of the sparse metadata. And concretely, let's consider the sparse matrix multiplication example. So here I show all 6 data flows of sparse matrix multiplication on one sweet sparse matrix. And here I want to show that picking the wrong data flow can actually lead to an almost 2 orders of magnitude performance difference. And so this performance implication really means that if a designer or user chooses the wrong data flow, no other optimizations they do can get you back that 2 orders of magnitude on the hardware. And so as previously mentioned, there are many expressions we care about, okay, and there are many data structures we care about. But now to achieve this performance via data flow control, right, which shows up in these expression schedule combinations, they actually lend themselves to multiple backends that we care about, these hardware accelerators that we want to program. And so we designed SAM, or the sparse abstract machine, to be fully general to this. So it is general to all of the expressions in sparse tensor algebra, but it lends itself to multiple backend designs, so both fixed function and reconfigurable, because some fixed function ones are fixed to a specific data flow, and reconfigurable ones can do multiple data flows. And so, well, why do we even care about an abstract machine, right? An abstract machine is just a representation. Well, it's not only general for the input domain and also these backends, it's the perfect compiler IR or compiler target. So we also develop from high-level domain-specific languages from prior work, mainly the Taco body of work. We develop a front-end compiler called Custard to our sparse abstract machine. So it doubles as both a streaming data flow representation and a compiler IR. And then I'm going to go into some details about SAM, but this is an overview. Like, this is just an overview. If you have questions about it, you can come talk to me. So SAM represents data flow in 2 ways. It represents wires carrying data through streams, and then it represents modules that compute on the data streams through primitives. And so from a high level, the way we represent tensors as streams is that we are able to represent multi-dimensional tensors, including higher order ones, as flattened one-dimensional streams. And so here I show an example of a 2D matrix, and the one 2D matrix is converted into 3 streams combined. So there's 2 streams for the coordinates and then 1 stream for the values. And the streams have a unique representation in that they have control tokens to maintain the dynamic data shape. And when these streams are streamed back into memory, they actually then can recompress into canonical data structures that we care about, like CSR or COO. And so SAM, like I mentioned, supports all of tensor algebra. And this is done through the interfaces that we define for our primitives. And we call them interfaces because we don't actually care about what how a hardware designer implements these primitives. We only care about defining the interfaces and how they interact with the streams. And so the first primitive class iterates through multi-dimensional tensors through our level scanners. We're able to combine multiple tensors or merge them together through intersection and union. We're able to repeat operands over other operands through tensor broadcasting. We're able to compute on scalar elements and then also do reduction operations. And then we're able to assign the multi-dimensional result back to memory. And then it's not really important that you understand how this whole SAM graph works, but this complete SAM graph demonstrates that SAM is able to represent full end-to-end kernels. And so this is, again, for the sparse matrix multiplication example, and I'm just going to touch on a few things to note. So sparse matrix multiplication, specifically the row-wise or Gustafson's data flow here. So the contraction's in the middle. And the first thing is that our hierarchical streams with data flow through the wires, which are our arrows in the graph. Data flows through our computation spatially. And then hierarchical sparse iteration occurs by composing level scanners together. So one level scanner will stream through one dimension, and then multiple composed together will stream through multiple orders. And then these primitives are format agnostic, which means that you can actually, for the same interface, you can use different level formats. And we have intersectors and unioners, which actually merge streams together, and tensor broadcasting through the repeaters. And then once the metadata is processed, we get the values and perform our computation, and then we construct a tensor result and store it back. And one thing to note is that our reducer is actually a vector reducer. Because it's Gustafson's data flow, you have an outer level accumulation. And the main portion of the computation in these sparse applications is really the metadata processing, which we've seen in a lot of work in this room, but really this graph visually shows that this is the key part of the computation. And then I wanted to touch upon an inner product algorithm for sparse matrix multiplication, because you actually use the same primitives and the same streaming representation. All you have to do is recompose the graph. And so some key differences are now the reducer, instead of a vector reducer, is a scalar reducer. So it uses asymptotically less memory. And actually, the intersection is now at the last data flow level. So it's after 3 level scanners instead of just after 2, which makes it less performant because you're filtering later. And so, although I already explained how we have a front-end compiler, and we motivate the need for a compiler, for these accelerators, what you really want is actually a compiler that provides a clean abstraction interface. So this is kind of like LLVM-IR or a stable ISA. It allows you to develop your front-end compiler and have a shared unified front-end compiler, and decouples it from the hardware implementation on the back end. So you can do iteration of both independently. And so our front-end compiler, Custard, has an algorithm to SAM, which is very straightforward, which kind of shows that SAM is the natural representation for these data flow graphs. Again, we take in these domain-specific languages from prior work, so a format, a schedule, and an einsum. And we combine it to concrete index notation, which is just an abstract loop nest for sparse tensor algebra. We convert it then to a spatial representation of that concrete index notation. And then there's a one-to-one mapping between the spatial representation of your tensors and your indices to your actual primitives that you lay out in the graph. And then, although SAM is abstract, SAM can actually bind to real hardware targets. So we show that SAM, using our cycle approximate simulator, is able to recreate results from prior work, namely Extensor, which is an accelerator from MIT. And then also, we're also able to bind it to reconfigurable accelerators, so reconfigurable data flow accelerators and coarse-grained reconfigurable arrays. So this leads me to my follow-on work, which was presented at VLSI 2 days ago, which is we fabricated Onyx, which is a coarse-grained reconfigurable array, or CGRA, that has sparse support for the full domain of sparse tensor algebra. And so some background on CGRA architectures. CGRA architectures are reconfigurable tiled architectures. You can think of them similar to an FPGA, but they're coarser grained. So instead of working on 1 bit at a time, they work on one element, like 1 word size at a time, or they work on, for a vectorized unit, like n word sizes at a time. And instead of lookup table-based processing elements, you have actually ALU-like processing elements. And we use SAM to fabricate the sparse CGRA. So what we were able to do is take prior work, a dense CGRA architecture, implement SAM primitives in RTL, and then produce this Onyx CGRA, which has both sparse and dense application support. And so what this means is that you don't have to understand the primitives here, but there's basically an RTL implementation in Onyx for each SAM primitive. So SAM acted as the architectural specification in terms of streams, and Onyx acts as the implementation to SAM. And on top of that, because I said we decoupled the front-end compiler, Custard was actually used, and SAM was used as the application compiler for the CGRA. So to program the CGRA after it's been fabricated, you're able to actually reconfigure the CGRA and then reprogram it with different sparse tensor algebra expressions. And on top of that, we had to extend the compilation flow to use a more implementation-specific representation. and create a new lowering pass from SAM to that Onyx IR. And then on top of that, we get functional and performance verification practically for free. So here I show the SAM cycle approximate and functional simulator for the repeater block. Because it uses the same streams again as the RTL implementation in Onyx, you can run the simulator and run the RTL simulation together and check functionally if they're correct, and then also look at the cycle count and see where the bottlenecks are occurring in your RTL versus in your actual functional simulation. And the functional simulation is cycle approximate, which means it is optimistic, but you can still see where the big mismatches occur and then figure out how to improve performance in your RTL from there. And so we have some Onyx results, and there's a bunch of results, but we basically show on average that we're between 4.4 to over 500x more energy efficient through our energy delay product. And our CGRA can run basically 8 applications across a varied data sets.
You're supposed to be done with the talk too, but somehow I can't stop my time.
But I am also done with the talk. So in summary, I presented 2 programming systems and a Sparse accelerator for how we can program these Sparse accelerators and really bring them to high performance users or end users. Thank you.
Thank you. Questions?
Very interesting talk. Can you talk a little bit more about those repeaters you had in this stream of operations? Is there a danger if I have a sparse matrix and a dense vector where the vector is logically broadcast by actually repeating that physically, so materializing this dense vector, that you change the asymptotic behavior of this particular operation?
Yeah, that's a great question. So if you're doing it for a dense vector, we assume that dense vectors have random access so that you don't have to repeat across the dense vector. The repeating mechanism is really for broadcasting across sparse vectors.
Got it.
Yeah.
Thank you very much. My second quick question would be for the mosaic part, where you essentially outline certain primitives into accelerator calls. Do you do a fine-grained scheduling that, I mean, I have the accelerator available and the CPU available. If the accelerator is 2 times faster, then I should schedule kind of 2/3 of my data to the accelerator and 1/3 on the CPU to actually fully utilize everything.
Yeah, that's a great question too. In the mosaic work, the reason why we don't call it an auto scheduler, we call it an automatic search mechanism, is because it doesn't have any performance information. So it's only based on functionality of the sub-expression matching to the total expression that you want. And it will search and find all of the places and just enumerate the list. It won't give you a priority ranking, and it won't schedule based on runtime. So that we assume someone would build on top of the automatic search mechanism.
Awesome, thanks.
Thank you.
One more question. Okay, back there. Then we can get the file.
Thank you for your nice talk. And I was wondering, is it possible for SAM being plugged into existing high-level frameworks like Rapids, PyTorch, or other graph processing frameworks?
That's a great question. That's ongoing work. We are re-implementing SAM in the MLIR framework and trying to use Torch to MLIR to then implement machine learning end-to-end models through SAM that can then target reconfigurable accelerators.
And is it possible for the users to write his own compiler front end to maps the high-level operations to the SAM API?
Yeah, so there's a little bit of flux in terms of the MLIR front ends from end user code to MLIR, so that we assume is already provided. It's not like on us as the backend compiler writers, but you would be able to write your own pass as long as you hook into MLIR.
Thank you very much.
Okay, thank you. So now we'll start with the panel.